Alright, welcome back everybody. In this video we're going to look at how we find derivatives of inverse functions. Okay, but before we do that we're going to just kind of review a little bit of information that's important for us before we find the derivatives of inverse functions. We start with this theorem here. If f is a one-to-one continuous function defined on an interval, then its inverse function, f inverse, is also continuous. And this should make sense to us, if we have a function, this function right here, f of x, it's continuous. And what we know about inverses is that the inverse of this is going to be the reflection over the line y equals x. So it's going to look something like this. So as long as that first function doesn't have any discontinuities, the second one won't have any discontinuities either. Alright, so that's what that theorem is. Now it's important, there's a phrase used in here, one-to-one. So quick, let's go over what a one-to-one function is. Basically, we all know that in any function, for a particular x value, there is only one y value. Now what makes a function one-to-one is that when there is, for each particular x value, there's a unique y value. In other words, if the y value when x is equal to 1 is 4, that means that that y value of 4 doesn't correspond with any other x value in the function. Okay, so each x is mapped to a unique y value in a one-to-one function. So we'll go through this first example here quick about what is a one-to-one function and what's not. Imagine y equals x squared. This is not one-to-one because there are many places where there are y values in common for different x values. So this is not one-to-one. When we think about y equals x cubed, every x value goes to a unique y value. So yes, this is a one-to-one function. And y equals absolute value of x. This is not one-to-one, again, because we have x values that correspond to the same y value at many places in the function. And y equals e to the x looks like this. And yes, that is one-to-one. Every x value goes to a unique y value. And it's important for us to understand the concept of one-to-one when we're talking about derivatives of inverses, because we're going to only be able to use what we talk about with derivatives on functions that are one-to-one. Alright, let's go on to example 2. It says here you should know the relationship between the graph of a function and the graph of the inverse of that function from before you started learning calculus. This is really instructive for us as far as determining the value of the derivative of an inverse. Let's talk about the derivative of the function y equals x squared at the point 2, 4. And what I'm going to do is I'm going to only draw the right-hand side of y equals x squared. Because if I restrict the domain like this, then y equals x squared is a one-to-one function. And we're concerned with the derivative of the function at the point 2, 4. Now we know that the derivative for y equals x squared is 2x. And therefore, at the point 2, 4, we can just substitute 2 in there for x, and the value of the derivative is 4. And so the slope of the tangent line to the curve here through that point is going to be 4. And so let's go from this side. And so the tangent line to this curve at the point looks something like this. Okay, now the question that we have is how does this relate to the value of the derivative of the inverse at the point 4, 2, which is the mirror image point on the inverse function. from the original function. And just like the function itself is a mirror image over the line y equals x, the tangent line to this curve at this point will be a mirror image of the tangent line to the original function. So if I go ahead and draw that tangent line in, oh, got a little jump there. Well, you can see that that's one line, but it's the mirror image. And so if we think about what the value of the derivative is here, the value of the derivative of the inverse at this point is just the reciprocal of the value of the original function at the mirror image point. And we're going to use that in order to find the derivatives of inverse functions. All right, let's go over to the next page where we introduce our theorem. If f is a one-to-one differentiable function with inverse function g equals f inverse, and f prime of g of a is not equal to 0, in other words, it's not a 0 slope there, then the inverse function is differentiable at a, and g prime of a is equal to 1 over f prime of g of a. Now realize, because of the way we wrote this, we wrote g as the inverse function of f. So another way that we could write this without introducing the function g into the situation is we could write that f inverse prime of a is equal to 1 over f prime of f inverse of a. And we're going to use that in order to find derivatives in the next couple of examples. So let's start with example 3. We're going to find the derivative of the inverse at a if f of x is equal to x cubed and a is equal to 8. So the derivative f inverse prime of a is going to be equal to 1 over f prime of f inverse of a. So we need to do two things here. One, we need to find the derivative of f of x. So we'll find the derivative of that function. That's easy enough in this case. And the second thing we need to figure out is we need to figure out what f inverse of a is. So f inverse of 8 we're looking for. That means that we want f of x to equal 8, and we want to figure out what x value that occurs at. And so we substitute 8 in for f of x and solve for x, and that occurs at an x value of 2. So that's going to be my value for f inverse of a. So this is equal to 1 over f prime of 2, and we know what f prime is. It's 3x squared. So we can just go ahead and substitute 2 in there. And this is the value of the derivative of f inverse at a equals 8. All right, let's do example 4. I'm going to do the same thing, same idea. So we need to find f prime of x. So we'll take the derivative of this function. It's 3x squared plus 1. And then we need to find f inverse of a. So f inverse of 1, which means we're looking for the x value where x cubed plus x plus 1 is equal to 1. And I mean, it's not like this is a super easy equation to solve for x, but if we're observant, we can quickly find out that this happens when x is equal to 0. Because if you just substitute 0 in for x, for all of the x's in this equation, we get the statement that 1 is equal to 1. And so finding our derivative of our inverse function, we've got f inverse prime of a is equal to 1 over f prime of 0. And then we're going to put 0 into f prime. So that's 1 over 3 times 0 squared plus 1. And so my derivative ends up just being 1 over 1, or 1. And that's the value of the derivative, f inverse prime, at a equals 1. All right, this next example, we're not even going to have to worry about finding the derivative. We start from f inverse of prime of a is equal to 1 over f prime of f inverse of a. And in this problem, we want to find f inverse prime of 2, because that's our a value. And in order to do that, that's going to be 1 over f prime of f inverse of 2. And now, since I know that f of 6 is equal to 2, that tells me that f inverse of 2 is 6. So the value of this derivative is going to be 1 over f prime of 6. And we're told right here that f prime of 6 is equal to 1/3. And we can go ahead and calculate the value of f inverse prime of 2 that way. So this opens up the opportunity for us to find derivatives of inverses based off of tables of information that we might have about a function, just in case we encounter anything like that. All right, last example, same idea. We'll play it out here. We want to find f inverse prime of -8. It's equal to 1 over f prime of f inverse of -8. Because of this equation here, that f of 1/3 is equal to -8, that means that f inverse of -8 is 1/3. And then I can just take the f prime value that I'm given, and we find that the value of the derivative of the inverse at -8 is 1/2. All right, so this is a pretty quick, straightforward way for us to find derivatives of inverse functions, even if it's a function that it's difficult to find the inverse of, like the one in example 4, y equals x cubed plus x plus 1. That would not be the easiest function for us to find the inverse of, but we can still find the derivative of it at a point by using this particular theorem. All right, that's it for this video and this lesson, and I will see you all next time. Bye-bye.